Hi, I'm Josh, and this is Electronics Unscripted, where we take an unscripted and intuitive approach to DIY electronics. This is the final video in the series of power supplies. Previously, we just worked with Ohm's law and created just simple voltage drops, and then we created a full-blown linear regulator that was controlled by a PID control loop with a Raspberry Pi microcontroller. But we found that that circuit was not incredibly efficient. So what we're going to do now is we're going to work on a switch mode power supply. And switch mode refers to how you use the MOSFET. Now remember, the MOSFET is a field effect transistor, and in our linear regulator what we were doing is we were turning that field effect transistor partially on. So transistors are effectively switches. They turn current flow on and off, but they have what's called a linear regime. And we kind of abused that linear regime in our linear regulator to turn that MOSFET into a variable resistor, which created a variable voltage drop that we were able to control in a control loop with our microcontroller to target a particular voltage across the load. So we could use it to create step down from 12 volts to 5 volts, or 12 volts to 3 volts, or 12 volts to 7 volts. You know, it would control for whatever voltage that we put as a target, but we found that it wasn't a terribly efficient circuit. And again, that's because we weren't turning that MOSFET fully on, basically creating a voltage drop by creating heat in the MOSFET. And we saw that our MOSFET actually got quite toasty. What we're going to do this time around is use the MOSFET in the way that it was meant to be used. They're meant to be used as switches. They're meant to be either fully on or fully off. And the MOSFET that we have turns on when you give it a positive gate voltage. The MOSFET has 3 pins. It has a gate, a drain, and a source. And you put voltage across the drain and the source, and the gate controls whether or not there's a conductive path between that drain and the source. In order to turn that path fully on, we need to drive the gate at 10 volts above the source voltage. We need to drive it at about 22 volts. Now, when we did our linear regulator, we built kind of an ad hoc gate driver circuit where we created a PWM smoother to get kind of an analog level out of our digital out, and then we used an op-amp to amplify that up into the range where we could get the gate to conduct. But if you remember, we didn't ever really get that gate to fully conduct, and that wasn't the point. If it fully conducted, we would not have a 12 volt to 5 volt step down, we'd just have a 12 volt power supply. And that's not what you want. But here we actually do. We want this MOSFET to be either fully on or fully off. And we're going to control the amount of step down by how often it's on or off. Now remember, PWM stands for pulse width modulation. We have a duty cycle. So the pulse can be on for 10% of that duty cycle, or 20%, or 50%, or 75%. So the more that duty cycle is on, the higher the output voltage that we'll get out of this switch mode power supply. Like I said, we can't just create this ad hoc little circuit like we did with a linear regulator to do this, because we need it to turn fully on, and we need 22 volts to turn it on. So they make gate driver chips that know how to do this. They sense the source voltage and boost above it by 10 volts to give you a gate voltage that will turn the MOSFET fully on. So the first thing that we're going to do is we're going to take a little bit of a look at the theory of how switch mode power supplies work. So just walk through the diagram of what we're going to be building here and where the different components are. Basic intuitive approach to how the switch mode power supply steps down the voltage. Then we're going to wire up our gate driver IC and take a look at it without the MOSFET, because I think it's instructive to see how one of these gate drivers works in isolation and see how it actually boosts that source voltage. And then we're actually going to go ahead and wire up the entire switch mode power supply and try it out with a load. I wanted to talk a little bit about the design of the switch mode power supply. It's a relatively simple circuit and has 3 major components. It's got the MOSFET, which serves as a switch. It's got an LC filter, so it's got an inductor and a capacitor that serve as a low-pass filter. So what they do is they filter out the PWM, the pulse width modulation of this MOSFET. They filter all that kind of AC noise down to a DC voltage across the Vout. And then the other thing is that we have this freewheeling diode. So this diode conducts only in this direction and not in this direction. That's very important for the functioning of this switch mode power supply. Additionally, what we've done is we've wired in a microcontroller, the MCU here, that uses a PID control loop to sense the voltage out of this circuit and to change the gate driver PWM duty cycle in order to target a particular voltage out. So it's constantly reading the voltage that's coming out and adjusting the gate to hit the target voltage. The basics here are that we use this microcontroller to turn this gate on and off at about 250 kilohertz, and then we vary the duty cycle. So we have it be open for 75% of the duty cycle, we'll produce a higher voltage out here. If we have it open for 25% of the duty cycle, it will produce a much lower voltage across here. So we can think about this in terms of an analogy to water again. We can think about the 12-volt source here that we provide on the left-hand side of the circuit as kind of a large tank of water. And it has a certain level. And if you tap that tank at the bottom of the tank, there's a certain amount of pressure at the bottom of that tank. And if that level were higher, there'd be more pressure at the bottom of the tank. If that level were lower, there'd be less pressure at the bottom of the tank. So you can think about it as having like 12 volts of pressure. That's like how deep that tank is. And so there's a certain amount of pressure at the bottom of that tank that represents that voltage. And this MOSFET is kind of like a valve at the bottom of the tank. We can use it to let more or less water out. And this LC filter here is a secondary reservoir of energy. And so that's analogous to taking your big tank of water that's a large reservoir and squirting little bursts of water into a smaller tank. And we also tap that smaller tank at the bottom of it to provide the lower voltage that we need for our circuit. So our circuit, there's some sort of a load, a resistive load here that's applied across this voltage out that is drawing down from that secondary tank as well. So if we draw too much, that voltage in that secondary tank will fall, and we need to increase the flow from the 12-volt tank above it. So you can see these are all interacting in concert, so you can think of it as a large reservoir, a tank with water that has a controllable valve that lets water into a secondary tank. And what we're doing is we're constantly targeting a particular level in that secondary tank that's analogous to having 5 volts of voltage across here. Another intuitive way to see this is that you're creating a waveform that's only a 12-volt waveform that's only on a certain percentage of the time, and this LC circuit is smoothing that waveform and averaging it down to represent kind of the energy that's there. And if it's on only 25% of the time, there's only 25% of the energy there, and that results in a lower voltage here. Now, the dynamics of the way that this circuit works are kind of interesting. So what happens is when you close the MOSFET, so when I say close, that means it's conducting. When you close the MOSFET, the freewheeling diode prevents conduction in this direction. So basically, you can almost think of that as not existing. So when I close this, electricity flows in through the inductor and starts to charge the capacitor. But the inductor resists changes to current, and the capacitor resists changes to voltage. And those interact in a way that they slow things down, so they don't allow like a huge rush of current through here. And the inductor will take that current and convert it into a magnetic field in the coils and in the ferrite coil in the inductor. And then when I open this circuit, so basically there's no current flowing from the 12-volt voltage source, the inductor serves as almost like a flywheel. its magnetic field begins to break down and it converts that magnetic field back to current that drives in this direction, but now this freewheeling diode can conduct in that direction. So what the inductor does is continues to push current through this circuit even when that gate is closed. Basically, it helps to average through that duty cycle and increases the efficiency of this circuit tremendously. Now, one source of inefficiency in this circuit is this freewheeling diode. There's a voltage drop across any diode, and that bleeds off electricity. So you're going to eat some power in this freewheeling diode. And it's not a ton. I think it's on the order of like 5 or 10%. So one of the things you can do is you can replace this freewheeling diode with a MOSFET. So if you put a MOSFET here that switches in exact opposition to this MOSFET, you can get effectively the same role as the freewheeling diode. So you can switch it in such a way that we only conduct in this direction when this MOSFET is open, and we don't conduct in this direction when this MOSFET is closed. And the gate driver chip actually knows how to do this. It's actually got a high side, so this is the high side MOSFET. If you had another MOSFET in here, it would be called the low side MOSFET because it's connected to ground. And the gate driver chip knows how to drive both the high side MOSFET and the low side MOSFET, and it makes sure that neither of them are on at the same time. So if they're on at the same time, if both this MOSFET, and if imagine we had a MOSFET here, if both of them were closed, you'd have a 12-volt short to ground, and your circuit would not be very efficient at all. It could burn things out as well. This gate driver chip knows how to drive switch mode power supply MOSFETs. It has the circuitry and so forth to step up the voltage to actually drive those gates properly, to do it in a digital way with a PWM signal. I took a shot at wiring this up. Note I don't have the MOSFET wired into it. So there's some places where the MOSFET is supposed to be wired in, like right here, that I just stuck that to ground. This should allow us just to test this circuit and see what it does. So what we've got there is the yellow trace is the output of the microprocessor, and you can see it's hitting about 3.3 volts max. The blue trace is the output of the gate driver chip, and that's hitting 12.5 volts max. This chip has another trick, and I'll show that to you really quick here. I can switch my lead from measuring the output of the microcontroller to the low side gate contriver that turns on and off exactly opposite of the first one. This yellow and this blue trace are exactly opposite of each other, but the cool thing that this gate driver chip does is it makes sure that there's a gap between them. So you look there, there's a gap so that they're never on at the same time. If they were on at the same time, you get a short circuit to ground, basically. You basically short your power supply periodically. I've got the switch mode power supply working, although it's not in a controlled mode. What it's doing right now is I just have a fixed PWM percentage coming from the Raspberry Pi microcontroller that turns the gate on 30% of the time and off the rest of the time. Here's the configuration for the gate driver chip. I'll leave the information about that gate driver chip in the description. Wiring it up was a somewhat involved process. I did it wrong at some point, so now I've got this guy who I'm keeping upside down right there because he's dead. I don't really need, this thing just doesn't get hot in this mode, so I really don't need this heatsink here. This heatsink is just left over from when I was using the MOSFET in linear mode as a linear regulator. I don't need that anymore. It just doesn't get all that hot anymore. That's because we're using this gate driver chip. It produces a high enough voltage to turn the MOSFET fully on. Here you can see the lower one is the source voltage. So that's the basically the output voltage that feeds into the inductor and the capacitor. The top one is the gate voltage. You can see that the blue trace caps out at about 12 volts other than that spike, and the yellow trace goes up to about 22 volts, so 10 volts above the voltage of the source. And that's what you need to get that MOSFET to fully turn on. But let's look at efficiency right now. So we are pulling almost 0.4 amps here at a relatively low voltage, and that voltage is going to be directly proportional to our duty cycle. So remember, I got a 30% duty cycle, so the voltage that we're getting is lower, and it's roughly, I don't think that's 30% of 12. It's not exactly a linear relationship, and it can depend on the current as well. So if I turn this current down, the voltage goes up. If I turn the current up, the voltage goes down. We can get an idea of how efficient this circuit is. So if you see here, it says that it's currently pulling 0.8 watts. The entire circuit is pulling 0.95 watts. We can do the math and we can come up with the efficiency. So that's 85% efficient. That's over twice as efficient as our linear regulator. With a buck converter, you get kind of an amps amplification factor. Here, let's go to a half an amp. So this is 500 milliamps basically. So that's 500 milliamps, but if I look at my bench power supply, it's giving me 12 volts at 130 milliamps. We've got quite a lot more amperage coming to our load than we have coming out of here. The power is what's constant, not the amperage. Power equals volts times amps, and because the voltage is being stepped down, the amps are higher than they are over here because the voltage is higher. So the power is what's constant. If we want to look at the circuit here a little bit, I've tried as best as I can to clean this up. We've got some bypass capacitors. The stuff over on the other side here is basically the bootstrap circuit. So there's a capacitor and a diode and some pins on the chip and a feedback loop right here that comes from the source on the MOSFET. And what it does is it bootstraps the source's voltage up by 10 volts, that higher voltage, that yellow line on top of the blue line. Down here, we simply have our inductor, which is a coil of wire around a ferrite core, and our capacitor. So this forms an LC circuit that basically smooths the intermittent pulses of current from the MOSFET and turns it down into a constant supply of voltage. We'll see our relatively constant 5 volts there is the blue line. We are going to see at the 500 millivolt level, there is quite a lot of ripple on that particular one, and it's around the switching. So you can see kind of synchronized around that switching, at least 500 millivolts or more, maybe 750 millivolts of noise on that output. So we could do a better job of putting more capacitors on the output. For our purposes, this is instructive enough. And again, we have all the limitations of having built it on a breadboard. So one of the things that you'll find if you try and lay out a switch mode power supply on a PCB, you'll look at the datasheet for the regulator, the switch mode regulator, and it will have a suggested layout that actually takes into account a lot of these effects, loop currents and so forth, at the particular frequencies that are recommended for that chip. The next thing we need to do is get some active control on this circuit. So as it is right now, I've got a fixed duty cycle of 30%. As I change my load here, the voltage kind of goes all over the place. Now remember, originally we were targeting a 250 milliamp 5 volt load. So let's go for that to start. Then we should be able to change our target. So we should be able to target different voltages and different loads. And with active control, the PWM duty cycle should vary dynamically. And hopefully we can see it here on screen as well. Should vary dynamically so that we always hit that 5 volt target. I've got to go back into my program and adapt it slightly. Okay, so we've returned our program back to the state when it was targeting the linear regulator. So let's come in here and change this to 5.0 volts. The PWM frequency is going to be 100,000. And let's go take a look here. So current, oh yeah, I'm running an old version of this program basically. So we're going to come back here and just to make sure that we don't break anything, we're going to hard code our PWM output to 30% and run this version of the program. So this should get the output at least showing us the voltage that it's measuring. The code says it's measuring 11 volts, but I think that's because the math is wrong. So if we come in here, yeah, so we don't have 4 times anymore. So we're just going to do that and see if that gives us a better estimate of the actual voltage. So that says 2.69, 2.7. So you can see 2.69, 2.7 on the MCU output and 2.6 on the load, which I'm going to call close enough. I could put in a correction factor to make those nice. I'm just not going to worry about that. Now we should be able to engage this control loop. Let's see what it does. So let's go ahead and get rid of this hard-coded 30% output. I'm going to be ready to turn this off pretty quickly if it goes south. So let's see what happens. So let's look at this. That didn't work. What I don't understand is the device is not found. So what happened over here? Did I burn him out? I don't think I would. The Raspberry Pi Pico is actually really hot. I might have burned him out, and I'm not sure why that would have happened. What I did is I connected the voltage detector of the load voltage directly to the analog input pin, which was fine because originally we were doing a duty cycle that only produced less than 3 volts. And then I set it to target for 5 volts, and who knows, maybe something went wrong with the circuit, and the voltage went very, very high across the load. And I'm betting I might have fried my Raspberry Pi Pico. Yeah, it's getting warm to the touch just being plugged in. Oh, good Lord. I fried it. I fried my Pi Pico. Okay. Well, lesson learned. I should have plugged the voltage sense into here that has a voltage divider to ground. So when I so nonchalantly just deleted that code that multiplies by 4, that was really stupid, and it cost me $2. Okay. Well, this is fine. I've got plenty of Raspberry Pi Picos laying around. So let's go ahead and pry this guy out. We reset with a new microcontroller, and we're going to pin our PWM output to a very low value and go ahead and run this again. And, oh yeah, we're not actually connected here. And you'll have to excuse me for my ratty little USB cable. It seems to work, even though it looks like the ground is shielding is shredded. So we just uploaded it. Okay, so now it's saying the voltage is 0.3 volts, which is good. That means the voltage divider is working. So now if we go back to our code and say 4 times the ADC value, so that's saying 0.13 volts, but I think there's something else wrong with this. Maybe we're not actually getting the output into the chip. Oh yeah, we don't actually have the power on. That was good that I didn't turn that power on. And I'm going to turn this on very quickly and see what happens. We have very low voltage, 0.4 volts. It's not exactly right, but oh, you know what? My switching guy came undone. This is the fun of breadboards. Every time you move anything around, things go berserk. Okay, that looks much better. So I have 1.3 volts here at a half amp, and I'm measuring 1.46 volts when I'm doing the math on the voltage divider. So I'm not going to worry about that being off by that much. But now I should not burn out my Raspberry Pi Pico, because the maximum voltage that this sensing voltage wire can pick up is 12 volts. I'm dividing by 4, so that should give me at most 3 volts. But let's start out with a target voltage that's relatively low. I know I started out with 5 last time. Let's actually start out with like 2 volts. Change this PID control to actually use the PID controller. Hopefully I don't burn out another one of these. Let's also set the amperage to be pretty low. Hopefully if something goes wrong, it won't fry the microcontroller. Cool, let's go ahead and, boy, I'm scared. I think we're fine. Well, that's good. You can see it, and you can see the voltage slowly climbing up to the target. And there was some sort of a transient spike. I'm not sure what was going on there, but it's still, yeah, so it hits the, according to the microcontroller, it's reading 2.00 volts right now. I've got 1.94 on the load. So that's cool. And it adjusted that PWM waveform to target this particular voltage. So let's go ahead and target a higher voltage. Let's go for 5 volts. That's kind of cool. You can see it as the PWM cycle adjusts, the voltage goes up and down. That's pretty cool. So we're at 250 milliamps right now, and the gate PWM is still at about 50%. It's oscillating a little bit. So I'm going to go up to 0.5 amps or 500 milliamps. And there, you can see the PWM is now up to about 51%. So I had to open up a little bit more to provide that extra current. The MOSFET is super chill right now. It's actually like kind of cool to the touch. Let's go even higher. I don't know what that was. Did you hear that? Let's see where that hit. So 800 milliamps, that's good. This is fascinating. It's still relatively sensitive to gate PWM, like, you know, very, very small changes in the gate PWM level results in large changes in the current through this circuit. So now we're only up to 52% open, and that's the difference between, you know, a half an amp and 3/4 of an amp. Now let's see if we go even higher. Something is making a noise. That's probably not very good. That was like in audio frequencies, and I'm not exactly sure what that was. That could have been, that's probably bad. That's probably something arcing somewhere. I don't know what would do that and what would make an actual circuit make noise like that. That was cool, but a little scary as well. So we'll cap ourselves at like 750 milliamps for the circuit. Remember, the design goal here in all my parts picking was just 500 milliamps. So we've hit that target handily. That's great. Let's give it a target voltage of 9 volts. Okay, I'm gonna abort this one. I don't think he's gonna hit 9 volts. I'm not quite sure why. Oh, because it had to go to a PWM of 100% just to get up to like 8 volts. So we're maxed out. And again, it could just be the inefficiencies of this circuit. So it clearly can't go that high. Let's turn that back on again and see where it did get to. So about 7.63 volts seems to be the max. Let's go back ahead and put in just 7 volts as our target voltage. Well, so that's interesting. It's giving us 7 volts at 66% of PWM cycle. So let's try 8 volts. Again, we're capped out. So there seems to be like a little bit of a hard cliff here between 7 and 8 volts. So let's go for 7.5 and see what we can see. At 70%. Huh. It's interesting. I don't know. I think we might be hitting, there's some sort of cliff in the circuitry here, because it would, based on the gate PWM and the voltages that we're attaining, I would think that we would have headroom, but this tells me we're going to hit a cliff pretty quickly. But it's clear that we're not going to be able to go much higher than this 7.5 volts. Now, one thing that would be fun to do is maybe have it dynamically adjust the voltage so that we can kind of see that on the screen here. That'd be fun. So you can literally see the PWM cycle increasing as the voltage increases, and as the PWM cycle decreases, the voltage decreases. Isn't that cool? Wow, look at that. And it's oscillating between 3 and 6 volts. that incredibly noisy quote-unquote DC voltage. Let's see if we can increase that a little bit. Let's take it up to down to 2 volts and up to 7 volts and double the changes speed as well. As the voltage zooms up and down, the PWM cycle on the gate voltage goes up and down as well with it. So it's just really cool to see those two things associated together like that. Now, one other thing we can do is we could change the PWM frequency and see what happens here. So let's put that to 50,000 and see what effect that has on our circuit. That basically forced me to put more load on the circuit to get it to work. I'm not sure if I have an intuitive sense of why that is. While past Josh looks confused, editor Josh is going to explain what's going on at low and zero current in this load. At zero load, what happens is that the capacitor basically has no way of discharging, so the voltage grows effectively to the limit of the circuit. And the controller loop has no way to control that voltage anymore, so it ramps the PWM cycle down to 0 and the voltage still increases. So it gets confused and there's basically no way that it can control the circuit. At low loads, what can happen is that you get into something called discontinuous conduction mode, so DCM. So if you have a higher load, this pulls current into the inductor. So basically the inductor at every cycle, when the MOSFET switches on, current flows into the inductor and builds up that magnetic field. When the MOSFET switches off, it pulls current through from ground in the same direction in the circuit, breaking down that magnetic field, serving as a flywheel. But if you haven't pulled enough current through that inductor, it effectively can run out. The flywheel spins down to 0 and you get what's called discontinuous conduction mode. So it then also becomes hard for the circuit to regulate. We can lower that minimum load as we increase our PWM frequency. So because of that, because we switch that inductor faster and faster and faster, it has less time to get its current down to 0. So that's what we're seeing at a lower PWM frequency at that 50 kilohertz. We have so much dead time when that MOSFET is off that the current drops to 0. So the higher the switching frequency, the lower the activation current is for this circuit. That wraps up this test with a switch mode power supply. We were able to wire up a gate driver to properly switch our switch mode power supply, wire in the inductor and the capacitor, and generate a high efficiency circuit that's at least twice as efficient as our linear regulator was. Thanks for watching, and let me know if you have any questions in the comments.